Thank you very much. Can you hear me? Great, fantastic. Hello. Thank you to everyone for organising this at short notice. Good stuff. Yeah. Really good work. My name's Peter Westmacott. I work at Strategic Blue, and we can save you money on your Amazon EC2 instances. Just slip that in there. So today I'm going to talk to you about the Mandelbrot Set, and I'm going to do that because I really like the Mandelbrot Set. How many people know what the Mandelbrot Set is? How many people have rendered one themselves? Oh, a few. Good. Okay, but a lot that haven't, so my talk isn't completely wasted. That's great. I used to love rendering these at school when I was bored and didn't know what to do. So, the Mandelbrot Set. So, part one, we're going to start with a little introduction to complex numbers. So, numbers predate recorded human history, as far as we know. I think it's fair to say. Here are some numbers. The number, or the digit 4 in each of these three numbers has a completely different meaning because of its position in the number. 4 is smaller than 40, is smaller than 400. The first documented evidence we have for place-based numerical symbols is from about 3400 BC in Mesopotamia. But you can place these symbols on a line, and they kind of represent a continuous quantity, which is quite interesting. You can also continue this line in the opposite direction. This gives you negative numbers, and our first documented evidence for this is from the 9 chapters on the mathematical art from China in about sort of between 150 BC. You can also add in 0. This is first documented in the Brahmagupta from AD 628. But sometimes mathematicians discovered that they needed another number, and it wasn't really one of the numbers that they already had. They wanted the square root of a negative number. And you can't really have the square root of a negative number, because if you take a negative number and times it by itself, you get a positive number. And if you take a positive number and times it by itself, you also get a positive number. So how could you have a number that multiplied by itself to give a negative number? Well, you can't, but the maths kind of kept demanding it. So what mathematicians did is they reluctantly pretended that such a number could exist. And René Descartes christened this number, but he wasn't the first person to use it. He christened it I for imaginary. It was an imaginary number because they couldn't believe it was real. But, it turned out to be quite useful. But where would it go? Where would we put it on this number line? We can't put it on this number line, so it sort of goes next to the number line, which sort of implies a new axis of numbers that's perpendicular to the original axis, which kind of implies a two-dimensional plane of numbers. And so we get these things called complex numbers, which have a real part, 3, and an imaginary part, 2i, where I is this imaginary number that's the square root of -1. So we have these complex numbers. What can we do with them? Well, we can do maths on them. We can do addition, for one thing. So if we have two complex numbers, 1 plus 2i and 3 plus i, we can add them together, and we can get a new complex number. And here we've just added the real parts, and we've added the imaginary parts, and we've got a new number. And we can see in two-dimensional space that kind of makes sense as vectors in space. We can also do multiplication on these numbers. So if we've got 1 plus 2i and 3 plus i, we can do maths on this. We can do multiplication. We don't quite know what I is, maybe, but we can just treat it like an algebraic quantity. We don't know what it is, but we can multiply it out. We can take all the bits of the first complex number, multiply them out by each of the bits of the second complex number, and we get a big term, but we can simplify it down, and we get an answer. It's another complex number. The only thing that we do know about I is that it squares to -1. So if you can see the second term on the second line is 2i times I, well, the I squared is -1, so we just end up with -2. It simplifies it a bit. What does that look like geometrically? Well, here are those three numbers again, the yellow one and the blue one. Multiply those together to get the green one. And, what does it mean to multiply them together? Let's look at the magnitude, the size of these numbers. Magnitude is considered to be the distance from the origin. And it turns out that if we multiply 2 and a bit by 3 and a bit, we get 7 and a bit. So we've just taken the magnitudes of the two numbers, multiplied them together, and we get the magnitude of the answer. So that works out quite neatly. And what about the angles? Well, it turns out that's even simpler. If we add that yellow number, or that yellow angle, to the blue angle, we get the angle that reaches the green number. So that's all quite neat. So we've got a bunch of complex numbers. They exist in the complex plane. They're sort of two-dimensional numbers, and we can perform operations on them which will transform these points in two-dimensional space. Part 2, strange attractors. So to talk about strange attractors, we have to first of all talk about ordinary attractors. So here we have on the left a very simple system. It's a pendulum. And we can look at this pendulum, but sometimes people like to visualize systems in a slightly more abstract way. We'll take some variables from this system and we'll plot them in two-dimensional phase space, as it's called. So here we're plotting the speed of the pendulum, the speed it's moving at, and the angle of the pendulum. And this gives us what's known as a cyclic attractor. The system is drawn into this cyclic motion. It repeats itself on a regular basis. But there's another kind of non-strange attractor called the fixed point attractor. And here we have exactly the same system, but we've introduced one extra thing, which is some friction. And as you can see, the system is now drawn towards a single fixed point in the middle. But some systems are more complicated than this. There was someone called Edward Lorenz, and he was trying to understand weather patterns, and he came up with a simplified model of convection. It had 3 parameters, and it had an equation for the evolution of each of those 3 terms, each written in terms of the 3 parameters. And when he plotted this, he saw an attractor that looked more like this. So this isn't cyclic, and it isn't drawn to a fixed point. This is a strange attractor. It continues forever. It never repeats itself. The line may cross over itself, but in fact, this is really just a two-dimensional picture of a three-dimensional attractor. So the system actually never passes through the same point again. If it did, it would have to cycle, because these represent everything we know about the system. So if it revisited the same point, then it would be back on the same path again. But it never does that. And other strange attractors exist. So this is the Lorentz attractor. Here we have a de Jong attractor. And also the famous French mathematician Henon produced the Henon attractor. And I think I've got a picture of a Henon attractor here somewhere. There's a Henon attractor. Sorry. There's a Henon attractor. Now, artistically, with these attractors, it really doesn't matter what starting point you choose within a certain bounds. If you pick some starting point, it will end up on the same path, but the path will have these same strange fractal properties. They repeat their themes at different scales, but they never cycle. But from a predictive standpoint, if you want to know where the path of your system is going to be at a certain point in the future, your initial conditions are very important. These systems have a strong sensitivity to initial conditions. You can start them in 2 places that are very, very close together, but at some point in the future they may have diverged a pretty much arbitrary amount. Colloquially, this is known as the butterfly effect, and this does tie back to Lorentz's work on weather systems that I mentioned earlier. There is a variant on this idea, though. Instead of taking one point, as we've done with these attractors, and iterating that one point to see where it goes, you might ask the question, what happens if we take every point in the system and iterate them all and see where they all go? And one very famous system like this is the Mandelbrot set. So in that, we say, the Mandelbrot set. In that we say, let's look at every point we have in this system and see where it goes. Does it either stay close in local space, or does it disappear off to infinity? So here, we can see a Mandelbrot set rendered, and the white area corresponds to points that remain local, and those are said to be in the Mandelbrot set. And the black area, these are points that, after a few iterations, they grew very large, and we could see that they were heading off into infinity, and they weren't going to come back. So we stopped worrying about those. So how does that work? Well, the Mandelbrot set exists in the complex plane, which is why we needed to introduce complex numbers earlier. Here we have some axes for scale, and we have a formula. So for each iteration of a point, we're going to take the point as it currently is, Zn, we're going to square it, and we're going to add a constant, and that will give us a new version of the point. So for each iteration, we'll square the number and add a constant, which will be a complex number, c. So typically we'll start with 0 as z value of 0, and c will be some number in the complex plane, and we'll iterate that, and we'll see if it stays local or if it goes a long way away. Now interestingly, the Mandelbrot set, we get a very wiggly shape. It's so wiggly, in fact, that although it fits entirely within a circle of radius 2, the boundary is infinitely long, which is kind of weird if you think about it. And the wibbly edges that give it a kind of a fractal self-similarity, and there are lots of images that exist of this. And most of these images work by doing the iteration and counting how many iterations occur before the value of z becomes really, really large. And they colour the image based on the number of iterations. And what that really means is that most of the brightly coloured images that you see, the coloured bands are actually the numbers outside the Mandelbrot set, and we're just counting how quickly they escaped. So let's see some examples to just make sense of this, so we all understand where we're going, because there's going to be some live coding soon. I want you all to follow along. So let's start with a C of -1 and see what happens. So -1 is our complex number. We'll start at 0 for z, and we'll see what happens. So first of all, we're going to square that 0. It doesn't do very much. And we'll add our complex number, -1. So now we've jumped to a z of -1. You all with me so far? Great. And then what happens? Well, we'll square that -1, and we'll get 1. And we'll take 1 off it, and we're back to 0. So we don't really need to iterate this number anymore because, well, it's already in a loop. It's gone from 0 to -1 and back to 0 again. So for our complex number of -1, we can iterate this as many times as we like with this formula. It will never escape to infinity. We know that this is deeply inside the Mandelbrot set. It can't escape. Let's try a different number. A half plus a half I. Let's see where that goes. Well, it's not getting too big. Oh, it's getting bigger. No, it's gone. No, that one's outside the Mandelbrot set. Let's try another one. -0.6 plus 0.6i. Oh, it's doing a lot of looping around. I think we might be all right. Yeah, that looks like it's cycling, doesn't it? Oh, no, wait, hang on. Oh, no, it's gone. So, now it's live coding time. Let's see if we can render a Mandelbrot set. Let's give it that. Oh, does that work? It's very exciting. Hello. Hello. Can you hear me? Yeah. Great, fantastic. So we're going to code a Mandelbrot set renderer. So the first thing we're going to need is to do some maths on complex numbers. So let's start by saying, well, we're going to need to add complex numbers. So we'll have an add function. And we're going to add two complex numbers, A and B. But what are our complex numbers going to be? How are we going to represent those? Well, I think the most idiomatic closurian way to represent them would be as a vector. So we'll have the real part of A and the imaginary part of A, and we'll have the real part of B and the imaginary part of B. And we'll add those together to create a new complex number, which will be a vector of the sum of the real part of A and the real part of B, and the sum of the imaginary part of A and the imaginary part of B. So I hope that's fairly clear. There are faster, more performant ways to represent complex numbers, but I think this will work for now. We also want to be able to multiply complex numbers, and for that we're going to have a function. It's going to take the same signature as our add method, not surprisingly, but the maths is going to be slightly different. So for that, we're going to start by adding up the multiplication of the real part of A and the real part of B. Add to that the multiplication of the imaginary part of A with the imaginary part of B. But of course, the I term is going to negate that second term of the imaginary part of A times the imaginary part of B. We need to negate that, so we'll just make that negative instead. And then we're also going to add up the other remaining terms. We'll take the real part of A times the imaginary part of B, and the imaginary part of A times the real part of B. That should give us a function that multiplies together complex numbers. So, the other thing we need to do, if we can do maths on complex numbers, is we're going to need to know whether they're still staying bounded in local space or whether they've got too big. So we're going to need a function that says, are these numbers big or are they kind of smallish? So we'll have a smallish function. Again, we'll operate on a complex number. Sorry, not A and B, real and imaginary. I apologise for the short variable names. Now, the magnitude of the number, we can use Pythagoras' theorem. We know that a squared plus b squared is c squared. So if we just add together the real times the real and the imaginary times imaginary, then we've got a squared plus b squared. So that should be c squared, hypotenuse squared, and we can take the square root of that. That gives us the size of the number, and then we can just say, well, is that number less than 2? If the size of it's less than 2, then it's a smallish complex number. And that'll be good enough for what we want to do. So now we're going to start trying to iterate these complex numbers. So we'll need a function to do some iterations. We'll call it iterations. We'll take a complex number c, and we'll start our iterations at the origin, 0, 0, and then we'll iterate over that with a function. We'll iterate over that with a function, and what will we do? We'll take each value, we'll multiply it by itself, so we've squared it, and then we'll add on our constant c. So that there is our z maps to z squared plus c. That's the function for our Mandelbrot set. We'll iterate with that. And then, what are we going to do? Well, we want to know whether it goes off to infinity or not. So we'll just take some of these numbers. We'll take the ones that are smallish, and then we can count how many there were. But of course, for the numbers inside the Mandelbrot set, they might stay smallish forever. So this at the moment is going to give us an infinite sequence, a lazy infinite sequence, and we can't really count that without bad things happening at the record. So we'll just take 100 of those. So that's going to be our iteration limit. We'll take 100 of those, and that's going to be a sequence of smallish numbers that we've iterated. We'll see how many of them stay smallish. And if they stop being smallish, then the sequence will stop. We count the sequence to know what colour we're going to make that part of our final image. So now, speaking of a final image, let's make an image. Let's have a function to render a Mandelbrot set. And we'll take the size, because I'm not quite sure what resolution we're working at here, so we might need to adjust that. And we're going to need some sort of canvas to draw on. Now, I've pre-prepared the canvas code separately, because we're going to be line coding that as well. It's a bit much. But it actually looked quite a lot like some of the code you may have seen earlier on some other slides to do with rendering. So we'll have a new canvas, we'll give it a title and a size. That should be quite straightforward. And then what we're going to do is we're going to iterate over every pixel on our canvas. The X position and the Y position for the group pixel. So range size. No, not alpha. So this is going to pass over every X and Y value, or every combination of X and Y values on the canvas. And then we will have we'll need a complex number that relates to each pixel. So we need to map from the pixel to a point in the two-dimensional complex plane. So we have a real part of that, and we will need an imaginary part. We'll come to that in a moment. So what we'll do is we'll take the X value, and the first thing we'll do is we'll divide it by size. So now instead of being a number from 0 to size, we've now got a number from 0 to 1. And then we'll subtract a half, so we've got a number from minus a half to a half. And then we'll times it by 4, so we've got a number from minus 2 to 2. If you remember, the Mandelbrot set I said earlier fits entirely within a circle of radius 2, so that should be a reasonable range to see the Mandelbrot set. And for the imaginary part, we shall do exactly the same thing, except we shall base it on the value of y instead of x. And then our complex number c is just the vector of the real and imaginary components that we've created. So now we're ready to do some iterations and pick a colour. So let's say, what's the iteration count? We'll count the iterations of C. That's hopefully very straightforward. And I've also got in my draw library palette of colours, which will hopefully make things fairly straightforward. So we'll take the nth value from that palette based on the iteration count, and that will give us a colour. So now we're ready to actually draw the pixel. Onto the canvas, and we'll draw it at position X, Y, and we'll draw it in the colour that we calculated. A bit more white space than we need there. And hopefully this all loads in the render. It does. So hopefully now we can draw render a Mandelbrot set. I don't know, how big do you think the screen is? Let's try 500 and see what we get. So we have there a Mandelbrot set, or a very colourful picture that includes the Mandelbrot set. Ordinarily, though, when one's rendering these things, the set itself is not rendered in one of the colours that you might have on the outside. So we can tweak this and say, let's make a slight change to the colouring. Let's say if the iteration count is 100, then we know we hit the limit. And we're going to assume that when we hit the limit, our starting point was inside the Mandelbrot set. So in that case, we'll say colour / So then if the iteration count was the limit, if we were writing dry code, we should probably extract that out because we've used it twice now. But then hopefully, yeah, one where it's black and then code. So there's a Mandelbrot set. This is a bit smaller. Make it a bit bigger. How much bigger do you think? Maybe double the size? Nice. You'll notice it slows down when there's lots of black pixels because, of course, we have to iterate those more, so it takes longer. Yeah, another note on performance. Using vectors like this, I think we're probably throwing a lot of vectors in the garbage collector here because we're creating them and destructuring them and so on. You can make this run quite a lot faster, even in Clojure, by doing other things. You can have depth records, that works quite well. And obviously, if you're doing a lot of primitive maths, then some primitive typings can help as well. So this isn't the fastest way to do it, but it's quite idiomatic. I think it's quite straightforward. It's fun. I hope you've enjoyed it. And one of the things I really like about rendering Mandelbrot sets is it's not too much code, it's not too much complexity, but when you come to a new programming language, it's quite a nice way to try out various things, looping structures, maybe try some recursion, see what the graphics libraries are like, the kind of things I like to play with, make Mandelbrot sets quite a good toy to play with. So thank you very much. Do we have time for questions or not?
Yes, we've got lots of questions. Anybody have any questions?
Questions? Oh, there's one there.
Yeah, I'm interested to know how far you've taken this in your explorations.
How far?
Yeah, I mean, kind of, how far have you delved into the Mandelbrot set?
Oh, not very far. Just enough to get pretty pictures. That keeps me happy.
Any other questions? You're just really hungry for pizza.
I know I am.
Oh, there we go. There's one more.
What would happen if you changed the 100 to a much smaller number?
Oh, we'd get fewer layers, but we can try that if we want. 10, does that suit? Yeah.
Okay.
So we can see we've got green, blue, pink. got about 10 layers there. And then it stops and you get a much more approximate wibbly shape. It's an approximation of the Mandelbrot set. A lot of that pink area will be in the Mandelbrot set, but quite a lot of stuff around the edge won't be from a pure mathematical definition of the set.
Thank you.
Any more questions? Any more? Don't want more?
Of course, if you want to zoom in on this image a lot, then you need that number to be quite a lot higher, because when you zoom in, you start to hit that limit. You can also hit limits with the precision of your computer's ability to represent numbers, or your programming language's ability to represent numbers.
Cool, great. Oh, well, thank you very much. Another big round of applause, please, for Peter. Thank you very much.